Hi guys, welcome to A Square Maths by A2E2. My dear friends, today we are going to study Calculus of Variation Part 1. Here we have taken different integral from x1 to x2 of f of x, y and dy by dx with respect to x. Here y is a function of x and dy by dx is a derivative of y with respect to x. Kindly note that dy by dx can be written as y dash. Here, if you want to maximize or minimize this function, we have to choose or we have to find the suitable value of y. Whatever the value of y is equals to f of x that maximize the integral is also called as extremal or stationary value. Kindly note that the equation 1 is also called as the functional. For example, if s is equals to 2 pi integration from x1 to x2 under y under root of 1 plus dy by dx the whole square with respect to x, and if you want to extremize this integral, let us choose the point a from x1 to x1 y1 and b x2 y2. Then to extremize this, we find the curve passing through a to b such that it minimizes the value of integral. Dear friends, for that one condition has given to get the maximize or minimize value of y. That condition is called as Euler Lagranges equation. We say that y of x is an extremal of this functional if the integrand f of x satisfies the equation dy by f by dy by y minus d by dx dy by f by dy by y dash is equals to 0. Dy by f by dy by y is a partial derivative of f with respect to y. Here is dy by f by dy by y dash is the partial derivative of f with respect to y dash, and d by dx is the derivative of this term with respect to x. Kindly note that this equation is called as Euler's equation or Euler Lagrange's equation. If this equation dy by f by dy by y is 0, that is f is free from y explicitly, then your Euler equation will be the d by dx dy by f by dy by y dash is equals to 0. After integrating with respect to x on both sides, you will get here dy by f by dy by y dash is equals to c, where c is a constant of integration. Second form of Euler's Lagrange's equation is the above equation can be modified as dy by f by dy by x minus d by dx f minus y dash dy by f by dy by y dash. As in the just like a previous case, if f is free from x, this derivative will be the 0 and this term will be only this term, and if you integrate with respect to x, that one will be the f minus y dash dy by f by dy by y dash is equals to constant of integration c. Third form of Euler Lagrange's equation, dy by f by dy by y minus dy by 2y by dy by x dy by y dash minus y dash dy by 2f by dy by y dy by y dash minus y double dash, that is second order derivative of y with respect to x deva 2f by deva y dash square is equals to 0. Let us see some problems on this extremals. First problem is find the extremal of integration from x1 to x2 1 plus x square y dash. So solution, let us take the integral I is equals to integration from x1 to x2 1 plus x square y dash bracket complete y dash with respect to x. Let us take whatever the integral is equals to f. So f is equals to 1 plus x square y dash into y dash. I can multiply both the terms or y dash, or I can make it free from bracket y dash plus x square y dash square. To apply Euler Lagrange's equation, I will have to differentiate f with respect to y and y dash partially. So partial differentiation f with respect to y dash is derivative of y dash is 1 and derivative of y dash square is 2y dash. X square will be treated as a constant as per as partial differentiation with respect to y dash concerns. And since f is free from y, derivative of f with respect to y partially is equals to 0. So by Euler's equation, we have deva f by deva y minus d by dx deva f by deva y dash is equals to 0. It implies that deva f by deva y dash is 0. I will put deva f by deva y dash, which I have found already, and d by dx. Since d by dx 1 plus 2x square y dash is equals to 0, integrating on both sides with respect to x, we get 1 plus 2x square y dash is equals to c. It implies that whatever 1, I'll take this side, that will be a 2x square y dash is equals to c minus 1 is equals to, let it this term is c dash. In next step, whatever 2x square, I took this side, so I got y dash is equals to c dash upon 2x square. But y dash is nothing but dy by dx. So dy by dx is equals to whatever the denominator x square will be the x to the power minus 2. Integrating on both sides with respect to x and y, we get here integration dy is equals to c dash by 2 integration x raised to minus 2 with respect to x. Since c dash by 2 is constant, will be outside, plus constant of integration c2. Integration of x raised to minus 2 is x raised to minus 2 plus 1 minus 2 upon minus 2 plus 1. Since integration of x raised to n dx is equals to x raised to n plus 1 upon n plus 1. Now in the next step, whatever the this minus 2 plus 1 will be minus c dash upon 2 will be replaced by c1 by x plus c2. This one is required answer. Next example, find the extremals of integration from x1 to x2 under root of 1 plus y dash square upon x into dx. Solution, whatever the integral, we have to extremize. Let it be I is equals to integration x1 to x2 under root of 1 plus y dash square upon x dx. Therefore f is equals to under root of 1 plus y dash square upon x, and that is equals to 1 by x 1 plus y dash square raised to 1 by 2. Deva, then we have to Differentiate this with respect to y and y dash. Since this term is free from y, so there is no point to differentiate it with respect to y. Let us differentiate it with respect to y dash. Therefore, partial differentiation with respect to y dash is del by f by del by y dash is equals to 1 by x as it is, and derivative of this term f of x raised to n is n, that is 1 by 2, 1 plus y dash square, 1 by 2 minus 1, that is minus 1 by 2, and derivative of y dash square is 2y. So if I simplify it, I will get y dash 1 plus y dash square raised to minus 1 by 2, and 1 plus y dash square can raised to minus 1 by 2 can be written as 1 by x y dash upon under root of 1 plus y dash square. By Euler's equation, del by f by del by y plus d by dx del by f by y del by y dash is equals to 0. By putting values, del by f by del by y is equals to 0 since the integrand is free from y. So minus d by dx, I'll put del by f by del by y dash. This is 1 by x y dash 1 plus y dash square raised to 1 by 2. After integrating this term with respect to x, this one will be as it is, and integration of 0 is only constant of integration c. So after integration with respect to x, we get 1 by x y dash 1 plus y dash square raised to minus 1 by 2. Here has to be minus 1 by 2 is equals to c. So by taking this x this side, this will be a cx, and by the law of indices, this one will be the to the RHS 1 plus y dash square raised to 1 by 2. Squaring on both sides, we get y dash square c square x square 1 plus y dash square. Taking this y dash square term to this side, but this term is multiple to c square x square, we get y dash square minus c square x square y dash square is equals to c square x square. So we get, taking y dash square common from this term, we get 1 minus c square x square y dash square is equals to c square x square. After taking this x term to this RHS, y dash square is equals to c square x square 1 minus c square x square. Taking square root on both sides and replacing y dash by dy by dx, we get dy by dx is equals to cx under root of 1 minus c square x square. On integration on both sides with respect to x, dy by dx is nothing but y, and integration of this term cx upon under root of 1 minus cx square dx plus constant of integration we have taken c dash. To find the integral, let us put 1 minus c square x square is equals to t. So it implies that minus 2c square x dx, derivative of this term dx is equals to dt. So it implies that x dx is equals to minus dt upon 2c square. But 1c is here, so it will be a minus 1 by 2c 1 by root t dt plus c dash is equals to minus 1 by 2c integration of t raised to minus 1 by 2 is t raised to 1 minus 1 by 2 1 minus 1 by 2. 1 minus 1 by 2 is 1 by 2. This 1 by 2 will get cancelled with this 2, and this one will be the, and t raised to 1 minus 1 by 2 is 1 by 2. So t raised to 1 by 2, t will be replaced by, that is under root of this minus sign is, that is, it is required answer. Next one, using the relation that the length of the arc between points ax1 y1 and b y x2 y2 is given by s is equals to x1 x2 under root of 1 plus y1 dash dx. Show that the shortest smooth plane curve between 2 points on a plane is a straight line. This sum is different from previous two. It is a less just like a descriptive sum. Here we have given the formula relation between the length of the arc between 2 points A to B has given, where coordinates of A are x1 y1 and coordinates of B are x2 y2, and here we have to show that the shortest plane curve between 2 points on a plane is a straight line. So we have, let us take this is equals to I as usual. It implies that integrand is equals to f under root of 1 plus y dash square under root of can be written as 1 plus y dash square raised to 1 by 2. Since f does not contain x explicitly, so and does not contain y also, so dA by f by dA by y dash is equals to, as usual, 1 by 2 f of x as it is, n minus 1, here n is equals to 1 by 2, 1 by 2 minus 1, and derivative of 1 plus y square by chain rule 2y dash, and this is 1 plus y square raised to minus 1 by 2 can be written as, this 2 will get cancelled with this 2, y dash upon under root of 1 plus y square. By Euler Lagrange's theorem, since f does not contain x explicitly, so we should use the corollary, that is f minus y dash dA by f by dA by y dash is equals to c, and after putting these values, this one is nothing but f minus y dash dA by f by dA by y dash. So to simplify it, taking LCM under root of 1 plus y dash square, this is under root of 1 plus y dash square into under root of 1 plus y dash square, that one will be the 1 plus y dash square, and this one is y dash into y dash is y dash square. This plus y dash square minus y dash square will get cancelled, and this one will be a 1 upon under root of 1 plus y dash square is equals to c. Squaring on both sides, you will get here 1 upon 1 plus y dash square is equals to c square. Taking reciprocal, this can be written as 1 plus y dash square is equals to 1 upon c square is equals to c1. Taking this one this side, so this one will be the y dash is equals to, and taking square root of y dash is equals to under root of c1 minus 1, let it be b, as good as it is constant, so dy by dx is equals to b. After integrating on both sides, you will get here integration of b, constant is x and constant of integration is a, so y is equals to a plus bx, and it is nothing but the equation of line, hence the proof. Next sum, find extremal of integration x1 to x2 y plus y square upon y dash square into dx. Solution, let f whatever integrand 1 plus y square upon y dash square. Kindly note that whatever the integrand is free from x, so differentiating f with respect to y partially, y dash partially, so 1 plus y square will be treated as constant, and derivative of 1 upon y dash square, that is y dash raised to minus 2 is y dash raised to minus 3 and into minus 2. Derivative of x raised to n is x raised to n minus 1 into n, just like that one. So this one is the derivative. And then since it is free from x, you are supposed to use the another form of Euler Lagrange's equation 6. So this one will be f minus y dash del by f by del y dash is equals to c, putting the values, and then this one will be a 3 because this one is 1 and this one is twice, so this will be a 3, 1 plus y square upon y dash square is equals to c. Taking this 3 this side and y dash square this side, then after this taking square roots on both sides, and whatever c by 3 will be replaced by c dash 1 by c dash is c1 here, constant of integration. Then this term I'll take divide by dy and c1 into dx, integrating on both sides. Integration c1 dx is equals to integration dy under root of 1 plus y square plus c2. And you know very well, integration of this term with respect to y is hyperbolic sine inverse of y plus constant of integration c2. And if you simplify, we get y, this c2 dash, c2 minus c2 is plus c2 dash, and this one y is equals to hyperbolic sine c1x plus c2 dash. It is the required answer. Next problem, kindly note that in this problem boundary values has been given. Integration from 0 to pi y dash minus y square dx, given that for x is equals to 0 y is equals to 1, and for x is equals to pi by 2 y is equals to again 1. We have integral from 0 to pi y dash square minus y square dx. Let us take integrand as a f. In differentiating this with respect to y and with respect to y dash, we get del by f by del by y is equals to minus 2y, and del by f by del by y dash is equals to 2y dash. Obviously, derivative of this term with respect to y dash is 2y, and derivative of this term with respect to y is minus 2y, since it is partial derivative. By Euler's equation, put the values. Del by f by del by y is nothing but minus 2y, and del by f by del by y dash is minus 2y dash. This is y dash is nothing but dy by dx, and this d by dx is y double dash, and this minus minus will become, this one is this one. Next, it is nothing but d2y by dx square plus y is equals to 0, and if you observe, it is nothing but the linear differential equation. And to find the solution, let us start from auxiliary equation. So it is d square plus 1 is equals to 0, and roots of the auxiliary equations are plus or minus I, and its solution is y is equals to c1 cos of x plus c2 sin of x. By using boundary conditions, y of 0 is equals to c1 cos of 0 plus c2 sin of 0 is equals to 1, implies that c1 is equals to, because cos of 0 is 1 and sin of 0 is 0, therefore c1 is equals to 1. And second condition, for x is equals to pi by 2, c1 cos of pi by 2, cos of pi by 2 is 0, c2 sin of pi by 2 is 1, therefore c2 is equals to 1. Hence y is equals to cos of x plus sin of x for this particular conditions. Thank you. If you like, kindly subscribe and share. To be continued in the next section. Let us see more sums on this topic. Thank you.